As you can see, this is our Chapter 15 review, Part 2, starting at number 22. First of all, can we cite an example? No, I'm sorry, cite an exception to the claim that all substances expand when heated. Well, one example that we have not discussed yet is some kinds of rubber material. If you apply heat to them, they actually shrink. You ever heard of shrink wrap? Shrink wrap is a plastic material that you put over a package, then they heat it up a little bit, and it actually shrinks and conforms perfectly to the shape of the item inside. You can buy this special film that you put on your windows. You use like double-sided tape to attach it all around your windows, then take a hairdryer to it, and it shrinks up and becomes so perfectly stretched and smooth that you can't even see it. I can't think what you call it, that shrink tubing stuff that you can put around electrical connectors. You solder two wires together, put this little plastic tube around it, and heat that up with a flame, and that tube will shrink up and seal your electrical connection very nicely. Some materials will indeed contract when heated, but most everything expands when heated. The most notable example, an example we've already talked about, is water between 4 degrees Celsius and 0 degrees Celsius. From 0 to 4, and only from 0 to 4, as you heat it up, it actually contracts. For reasons that we went through in a previous video, you can go back and study that again. But that happens from 0 degrees up to 4 degrees. It contracts, 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 contracts. When you get to 4 degrees, water is as dense as it's ever going to be. Then you continue to heat it up, and once again, once it hits 4 degrees, then it starts to expand again. So from 0 to 4, you heat it up, it contracts. Then from 4 up, it begins once again to expand. Number 23. If we had a bimetallic strip, first of all, let's review what a bimetallic strip does. Bimetallic strip is two different kinds of metals fused together. Very thin. I drew them thick here so we could see them, but in reality they're very thin. Do I still have my bimetallic strip in the room? I didn't think about that. Oh, I see it. Yes, I do have it. It's right here behind the camera. I'm not going to take the time to heat it up again for you. You saw that in the previous video. But this is one particular material, perhaps brass on one side, and it's something more silvery looking on the other side, maybe iron, steel, whatever. So this is a bimetallic strip, two different metals. When you heat it up, what happens? Apply a flame to this thing. The brass side is going to expand faster. The iron side will expand more slowly. Different materials expand when heated at different rates. Well, because the brass expands more quickly, it's going to try to stretch this way while the iron is saying, no, we don't want to. What's the result? It's going to actually curl up like this, as you saw it do when I applied a flame to this thing. Pretty cool. Now, what, however, would happen if the two metals expanded at the same rate? Well, hopefully that answer is obvious. If they both expand at the same rate, what's going to happen? Absolutely nothing. They'll both expand at the same rate. It'll get a little longer, but it will not curl. It will not bend. And I think that's all there was to number, lost my place, number 23, yes. Would it work? No, it wouldn't. Is it important that they expand at different rates? Well, yeah, otherwise it's not going to bend. Number 24. 24, here we have what he's talking about. You got two metal plates. You've got a hole drilled through the two plates, and you've got this rivet thing. That rivet starts out looking like this kind of. You put it through the hole, and you get it really, really, really super hot first. I mean red hot. You put it through that hole, and then you start pounding on this side. Because it's hot, it becomes more pliable. You hit it with a hammer, and it bends very easily. So as you hit this red hot rivet with a hammer, it starts to bend over like this. And you try to get it as close to looking like this as you can get it. Now, not that I've ever done this, but that's the idea. But it's still going to be kind of loose. Things are going to be a little shaky there, even though it's now been bent over. But because it was hot, what happens when it cools down? It's going to contract. As it contracts, what happens? It contracts this way, it pulls these plates together and makes everything get nice and tight. So having the hot rivets has two purposes. Purpose number one, you can bend over that side so it locks in. Purpose number two, as it cools down, it pulls those metal plates together, never to be separated again. Yes, the breaking boulders thing, number 25. You've got a big boulder. You're working out in the fields, and for some reason you want to break this thing in pieces. Maybe you need to have smaller pieces to carry them away. But you want to break this boulder. What can you do? If you can build a hot fire around that boulder and heat that thing up like crazy. Make that boulder really, really hot. And then, once it's nice and hot, throw some cold water on it. What happens? You put the cold water on the outside of the boulder. The whole boulder is already now hot. So now you've got the cold outside and the hot inside. The colder outside is going to want to contract, but the hot inside is saying, no, we're not contracting today. There's a conflict going on there. Something's going to break. As the outer part of the boulder contracts, it's going to start cracking, and that crack will probably just go right through the whole boulder. You might break the thing right in half, because the inside and the outside are going to be, the outside is going to be contracting while the inside is not. Same thing happens, we already discussed it in the previous video, same thing happens with glass. Put a hot liquid into, say, a glass jar. As the inside of the jar is heated up and expands, the outside is staying cool, relatively so, and is not expanding as fast. That difference in expansion rates will cause the glass to shatter. Don't do it. I always allow for instance, if I want to put grease into a jar, I let that grease cool off a good bit before I pour it into a jar, because I really don't care to have broken glass all over my sink and grease spilled all over the place. So don't pour hot grease into a glass jar until the grease cools down a lot. Let's see, number 26. You drive your car for some distance. What happens to the air pressure in your tires? It will actually increase. Why does the pressure increase? Because through friction, of rolling on the road for a long time, through friction, the air inside the tire and the tires themselves get warmer, hotter. What happens when air gets hotter? It expands, thus increasing the internal pressure. There's a lot more that could be said about air pressure in tires, but I think we may have addressed some of that back in a previous chapter. We're not going to go there now. But yes, hot tires will have higher pressure. That's why when you fill the tires with air, it'll say on that little label that's on the door frame of the car, it'll say cold tire inflation pressure. They want you to put the air in it when the tire is cold. If you put it in when the tire is hot, well, you're going to end up with the wrong pressure. You think you've got one pressure, but the tire cools off and you find it, oh, it's not a high enough pressure. So they want you to put the air in while the tire is cold, which is rather impractical, because most folks put air in their tires at a gas station, which they had to drive to, which warms up the tires. So how do you get a cold tire inflation pressure? I guess you let your car sit at the gas station for a couple of hours. I don't know, it's just not practical. Anyway, that's what they say to do. And that's why they say to do it. Number 28. Oh yes, creaking noises are often heard in the attic of old houses on cold nights. Why is that? Had some experiences back at Montrose before they demolished the old gym where Kevin Durant used to play. Yes, that gym is now gone, except for a few bricks that I saved at home. But I would be inside that gym alone at night sometimes, or not at night, that wouldn't work. Alone in the gym in the daytime, not at all uncommon. And you could tell when the sun rose to a point where it hit one side of the angled roof. Because when the sun rose to a certain point, it would heat up that metal roof, and that metal roof would begin to expand. The sun would hit the shingles were black asphalt, they would expand, they would heat up the metal roof would expand, and as that metal roof expanded, you could hear creaking and crackling sounds as the roof expanded. If you didn't know what was causing it, it would be a little bit unnerving. What's wrong with this building? Is there somebody in here with me? What's going on? Yeah, it's kind of weird. And it can freak people out in old houses, especially when the sun hits the house on a certain side or the sun goes down, things expand, things contract, and it causes wood to be rubbing against wood, and it causes squeaking and creaking. Something that happened to us when we first moved into our townhouse, 30 whatever years ago, a long time ago. Brand new house, we just moved in, and I noticed this weird drip, 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 drip sound in the wall. I thought, oh man, we've got a leaking pipe, the house is brand new, I'm going to have to contact the builder and complain. But I realized, wait a minute, there are no pipes in that part of the wall. The bathroom's over here. Kitchen's way down there. I'm up in the bedroom. I'm hearing this drip, drip, drip sound from the wall. There are no pipes there. What in the world is going on here? Well, it turns out it was not dripping water at all. There was a vent pipe that went from the basement, connected to the sewer line, a vent pipe that went through the first floor, through the floor there, through the second floor, through the ceiling, and emptied sewer gases into the air up there so it doesn't come into the house or cause any other problems. Well, what happens is, if you run some hot water in the house, like take a shower, run the dishwasher, washing machine, whatever, you run hot water, that hot water goes through the drain pipe, causes all the pipes in the house to expand. As those pipes expand, that vent pipe would then begin to move ever so slightly upward in the house. There was a wooden 2x4 in there between the floors, and that pipe was rubbing against that 2x4, going pop, 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 kind of like little earthquakes, where the pressure would build up and it would have to move and it would go pop, then the pressure builds up and it moves again, pop, and the pressure builds up, moves again, pop, and it was just going this rhythmic pop, 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 pop as the pipe moved past the board. Guy came to investigate our complaint, and he explained to us what was going on. All he did was tear a hole in the wall, and he stuffed some of that pink insulation stuff between the 2x4 and the pipe to enable it to slide freely instead of going pop, pop, pop. Now it could slide, and our pop, pop, pop was gone. It was not dripping water, it was just heat expansion. Oh, and he did fix the hole in the wall, by the way. You would never know he was there. He's good. He knew what he was doing. So yes, it's from expansion due to heating and contraction due to cooling. They both do the same thing. Number 29, related to that. If you got a couple of glasses here, and I've had this problem before, maybe you have also. You have two glasses that are nested. I drew this diagram in case you didn't know what it means to nest the glasses. You put them in together like that, and they sit down snugly together. Nice way to store them, except for one problem. Sometimes they'll get them like that, and they will be stuck. And you'll grab this outer glass and grab the top glass and try to pull them apart, and they're not coming to think, oh no, what have I done? I can't get them apart. A trick that will work. Go to the sink, get some hot water running. Run the outer glass, or this works with plastic as well. Run the outer glass under hot water. What happens? The outer glass will then expand while the inner glass does not. Once the outer glass expands, oh, can I illustrate with my electronics here? Once the outer glass expands, then it frees it up so you can remove the inner glass, no problem. It works. Same thing with the jar. You can do the same thing with the jar, a lid that's stuck. If you take that jar of pickles and run that lid under hot water, you can often get that lid to expand enough where it will be able to, you'll be able to get it off much more easily. All right, moving on. Real life physics. Number 33. I do have a pair of these things. I've got this little brass ball and a brass ring upstairs in the science lab. It just did not occur to me to bring them down with me. Oops. But as they are right now, it is difficult to impossible to get that ball to go through that ring. They don't quite fit. However, if you take that ring and put it over the flame and heat it up, if you heat up this ring, does the hole get smaller or does the hole get bigger? Does the metal expand both directions, both inward and outward, or does it all simply expand outward, making the hole bigger? Well, the reality is the hole gets bigger. The proof is in this device that I could have brought down with me, where you heat up that ring, and once that ring is heated, the ball goes through very easily. And if you put them together so the ball is sticking through the hole, and then let them cool off, once they've cooled down, it's really hard to get that ball back out again. Heat up the ring, and the ball will fall right out again. Yeah, let's move on. Number. There's more that could be said about that, but let's move on. Does the size, he said in 33, he asks, does the size of the hole increase, stay the same, or decrease? Well, if you heat up that ring, the size of the hole actually increases. Oh, he also says the other way around. What if you were to heat up the ball? Well, then the ball's going to not be able to go through the ring at all. Same thing. Reverse story. 34. Here's what he's talking about. We've got this chunk of brass here, a cylinder of brass, and it's cold. I think he uses the word very. It's very cold. Then he's got this hot iron ring, and he puts the hot iron ring over, and it's a snug fit. You got to kind of push it down there. The hot iron ring gets pushed down onto the cold brass cylinder. Then you let them cool down, or you let the hot iron cool down. When the hot iron cools down, it of course contracts. The brass is already cold, so it's not going to contract. So now that hot iron ring is very, very firmly attached to that brass cylinder, because the brass was already cold, the iron was hot, so the iron contracted and drew itself down really tight against that brass. So he says, you're not going to be able to get those apart again. Not without cutting something that's never coming apart again. Well, how about if you just heat up the iron and expand it again? You can't. Because guess what happens if you try to heat up the iron? The brass is going to heat up right along with it. And which one expands faster? The brass expands faster. The more you heat up the iron, the more the brass is going to expand. It's only going to get tighter because the brass will expand faster than the iron, and that brass cylinder is going to get larger and larger and larger, and only make that iron ring tighter and tighter and tighter. You can't get them apart. Next. Number 36. Do I have something for 36? Yes, I do. Okay. When a mercury thermometer is warmed, the mercury level momentarily goes down before it rises. For just a moment, you stick it into some hot liquid. For just a moment, the level of the mercury or alcohol or whatever will drop down a little bit before it starts going up. Why would that be? Well, because you put it into the hot liquid, it's going to take a little bit of time for that heat to go through the glass and get to the liquid inside. So since the heat is hitting the glass first, for just a moment the glass expands while the mercury doesn't. So the mercury falls down a little bit. But then in just a few moments, the heat makes its way into the mercury and everything starts to behave as expected again. But for just a few moments, in the very beginning, the glass expands first because it's in contact with the water, and that causes the mercury level to drop a tiny bit before everything heats up equally, and then the mercury starts to rise again. Moving on to number Last page, number 40. Yes, the plot of land question. It takes a little bit of thinking. This is kind of mental gymnastics here. It's a hot day. I think we started with a hot day, didn't we? Yes, we measure our land on a hot day. And we measure it, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 feet. We see our land is 17 feet long on a hot day. Now we come back and we measure it again on a cold day. What happens on a cold day? On a cold day, the tape measure is going to shrink somewhat. And no, the land is not going to shrink. Okay, let's just leave it at that. The land is not going to shrink. But the tape measure is going to shrink a little bit on a cold day. If the tape measure shrinks a little bit, if we keep the end of the tape right at this corner here, and the tape measure shrinks, then perhaps instead of this mark being here at the end, maybe it's going to shrink down to the point where, oh, hey, I can shrink this thing. Wow, use my electronics here. Let's group them. And now we can apply a cold day to this tape measure. So now if the tape measure shrinks on that cold day, and now I line up the end of the tape measure here as it was before, now I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Oh, now it says 18 feet. Oh, so on the cold day, my tape measure says my land got bigger. Did my land get bigger? No, my land did not get bigger. My tape measure got smaller. But I will now measure, on the cold day, I'll measure a larger piece of land, so I think. My measurement will say my land is larger. Surveyors, back in the old days before they used lasers to get distances between things, when they actually used a tape measure to survey land, to measure out land, they had to take into account the temperature on that day. They would have charts, books that would tell them, okay, on such and such a day, we have to multiply the actual length by this to get that. It would depend on the temperature of the tape measure. They had to take that into account to get accurate measurements. Number 41. What was the precise temperature at the bottom of Lake Superior at 12:01 a.m. on October 31st, 1894? How do I know? I wasn't there. Yeah, nobody was. But Lake Superior, it's pretty far north. We're not talking in the tropics. We're talking a place where water temperature rises and falls. Well, at what point is water at its densest? Water is the densest at 4 degrees Celsius. So when the water is at 4 degrees, it's going to sink to the bottom. It's going to stay there. Any water that's either warmer or colder is going to rise up higher, because 4-degree water is the densest water ever gets. So it's going to stay at the bottom. And it's going to stay at the bottom. In fact, it's going to stay at the bottom probably all year. You go to the bottom of Lake, what lake was this? The bottom of Lake Superior, I'm going to guess at any time of the year, and you'll find the water at the bottom of that lake will be at 4 degrees, because that's where dense water goes, to the bottom. That's why fish are able to live under ice, because you go down below the ice, the water actually gets warmer. Up to 4 degrees. Moving on to number, I'm lost, number 42. Suppose that water is used in the thermometer instead of mercury. Okay, so we got water in the thermometer instead of mercury. It's not going to work very well. Suppose we start at 0 degrees and we warm that thing up. At 0 degrees, we warm it up. What happens to the water in the thermometer as you warm it from 0 degrees upward? Well, remember, from 0 to 4, water does the reverse of what we expect. From 0 to 4, as you heat it up, it actually contracts. So if you have a thermometer that uses water, and the temperature is 0 degrees, and the temperature rises, the water is going to contract and it's going to go down. What does that tell you? Not much. the water level is actually going to go down as the temperature goes up. So here it would go down. Surprise, surprise, because water is weird. Between 0 and 4, water is weird. What happens if the water is already at 4 degrees and you warm it up? Well, from 4 degrees, as you warm it up, it does what you would expect it to. It expands. It goes back to doing what I would call normal things. From 4 degrees upward, it will expand. So the water in your thermometer will rise from 4 degrees. As you put more energy into it, it will go up. How about if you start at 6 degrees and warm it up? Well, again, at 6 degrees, you warm it up, it will continue to expand. It will go up. But from 0 to 4, water does the reverse of what you would expect. It actually contracts. It contracts as you heat it. It expands as you cool it. That's why ice cubes get bigger when you freeze them. That's also why, in fact, I think this is what the next question here is. Why is it important to protect water pipes so they don't freeze? If you've never seen this before, then you did not watch the previous videos. Shame, shame on you. This is that bottle that I found. It's made of metal. It's an aluminum, I think, bottle. And I found it in a freezer full of water. No, the freezer was not full of water. I found it full of water in the freezer. And I was shocked. It was not mine, but I took it because I liked it. I liked what I saw. What I saw was this. Full of water, it froze. What happens when water freezes? From 4 degrees down to 0, it expands. By the way, it doesn't suddenly expand when it freezes. Common myth, common misunderstanding. Water does not suddenly expand when it freezes. Water expands as it approaches 0 Celsius. Water expands from 4 down to 0, and once it's frozen, it stops expanding. It only expands as the temperature goes down from 4 to 0. Then, once it's frozen, it starts to contract again. But the water in this container, as it went from 4 down to 0 and approached that freezing point, it expanded and it cracked the bottle like that, becoming obviously quite useless, but very nice for an illustration of why you have to protect your water pipes in your house from freezing. If you have pipes that are exposed to cold air and you don't do something to protect them from freezing, or if you don't remove the water from those pipes, then when they get super cold, when they go from 4 down to 0 degrees, that water will expand and your pipes will crack. More on that in the old video, probably I'm going to guess part 3 of the videos, I don't recall. If you want to hear more about pipes in the winter, then check that out. It can be a very, very serious problem, costing multiple thousands of dollars in repairs if your pipes crack in the winter. That's also why if you have a vacation home, you have to empty all the that vacation home is vacant in the winter. My parents had a house in the mountains in West Virginia. They never went there in the winter, so they had to winterize the house. Part of the process of winterizing the house was to empty all the pipes of water, get the water out of the pipes. Because if you left the water in the pipes, you knew what was going to happen. You were going to have broken pipes all over the place. Not good. That's why they have to winterize houses that are not used in the winter. Okay, and that, I believe, is the end of that. Yep, we're done. So the next thing that you're going to have to worry about is the Chapter 15 test, and that will be coming to a computer near you very soon. So for now, that's all. We will have, at least for Covenant Life, we will have a Zoom review session coming up in a couple of days. So stay tuned for that. Farewell.